small time and space by variable.
Thanks for the introduction. So the topic of this work is the relationship between three fundamental computational resources: time, space, and randomness. So this is like a pretty classic, well-studied topic. So to be more specific, let's suppose some language L can be decided by a randomized algorithm that runs in time t and space s. Okay? And let's consider the regime of parameters where the algorithm has enough time to read the entire input, and the algorithm has enough space to store a pointer to anywhere in the input. Okay, then the question I want to ask is how efficiently can we decide this language by a deterministic algorithm? So one answer to this question is given by Clivens and Van Melkebeek, following a long line of work which says, if you're willing to assume circuit lower bounds, so if you're willing to assume that, let's say, linear space has exponential circuit complexity, then it follows that there's a deterministic algorithm for this language that's about as efficient as the randomized algorithm we started with. Okay, so in the process of de-randomizing, you only have to pay like a polynomial factor in terms of the running time, and you only have to pay a constant factor in terms of the space complexity. So for the purposes of this talk, the main defect of this theorem, the main downside, is just that it has this unproven mathematical assumption. Okay. So in this talk, we'd like to understand, like, what kind of de-randomization can we prove unconditionally? Okay, now that's also a classic, well-studied topic. There's been a lot of success in proving unconditional de-randomization theorems, especially by focusing on the space complexity of the deterministic algorithm. So just to give one example, here's a theorem by Nissan and Zuckerman. This is an unconditional theorem. This says, let's consider the regime of parameters where the space and time bounds are polynomially related. All right. In that regime, they show that there's a deterministic algorithm for this language L that runs in space O of S, optimal. Right? It's just like what we wanted. You just lose a constant factor in terms of the space complexity. Okay, now admittedly, it's not a fast algorithm. In fact, it's as slow as it could be given the space bound. But from the perspective of space complexity, this is a very nice result. Okay, but it does only apply in this limited regime of parameters when the space and time bounds are polynomially related. And unfortunately, this is not, this has never been extended since then to apply to a wider regime of parameters. So that's where this work comes in. So let's consider a different regime of parameters. Let's consider the case that the time bound is at most n times some polynomial in the space bound. Okay, and the most interesting case to think about is the case where the space bound is logarithmic. So then we're talking about de-randomizing log space quasi-linear time algorithms. So we're de-randomizing super efficient randomized algorithms. Oh, yeah, sure. What's the computational model? So let me not be super precise about the computational model, but it's like a random access model. Like you get query access to the input, which, yeah, good question. That matters when we're talking about, this fine-grained, this level of fine-grained time complexity. Okay, so the Nissan-Zuckerman theorem does not apply in this regime. But what we're able to prove still is that there's a deterministic algorithm for this language that runs in space O of S, optimal, okay. With a catch. And the catch is that our algorithm is only guaranteed to work on most inputs. On some tiny input, tiny number of inputs of each length, our algorithm will just give the wrong answer. Okay, so this is like what is called a typically correct algorithm. This is a typically correct de-randomization. So I want to be clear that, like, from a practical standpoint, a typically correct algorithm like this is just worse than the randomized algorithm we started with, right? It's if I may make an analogy, like a randomized algorithm is like, you're in a public place and you need to use the bathroom, so you pick a random stranger and ask them to watch your stuff. Most people aren't thieves, so this is a pretty reasonable course of action. Okay. In contrast, a typically correct algorithm is more like You're sitting outside and a stranger pulls up and says, "Get in my van." And you think to yourself, well, most people aren't kidnappers, so you get in, right? It doesn't make so much sense, right? That's not a smart course of action. Because I mean, really, the point of the story, right, is that it's too optimistic to think that you're going to get a typical input. Right? There's a reason that in computer science we generally make worst case assumptions, and we want algorithms that are guaranteed to work on all inputs. Okay. Okay. That being said, I hope you'll agree that from a theoretical standpoint, this is an interesting theorem. Right? It's sort of like transmuting gold into lead. Like, not exactly what we wanted to do, but I mean, something's going on. So I hope this. I hope this still tells us, something about de-randomization. Okay, and just for comparison, if you wanted an algorithm that works on all inputs, that's always correct, the best de-randomization for this, this setting of parameters, like log space quasi-linear time algorithms, the best de-randomization is this algorithm by Sachs and Joe that runs in space log to the 3 halves n. Okay, so in terms of the space complexity, we're getting like a power 1.5 improvement.
Is the time for your algorithm like QPS?
Yeah, that's right. The running time of this algorithm it's as slow as it could be given the space bound. Yeah, good question. All right, so let me start telling you about how to prove this theorem. Right, so we're trying to decide some language L, right? So we're trying to decide if some string is in this language, and we're only shooting for a typically correct algorithm. So we only need to worry about a typical input, like this one right here. All right? And what we have at our disposal, what we know is that there is a super efficient randomized algorithm for this language. So if only we had some randomness, then we could just simulate that algorithm. Okay, well that looks pretty random to me right there, right? So a really natural thing to try is to just try to use the input as a source of random bits. This is an idea suggested by Goldreich and Vigderson. So like the most naive version of this idea would be like, look, we have this randomized algorithm A. Let's just copy its input into its random tape. It's worth a shot. It's tempting to think that this should work for most x. But that reasoning is flawed. This might very well fail on all x. Because after all, a randomized algorithm generally isn't guaranteed to behave well if its input is correlated with its random bits. Okay, so in order to prove like any kind of typically correct de-randomization result, basically the game is we want to do something about these correlations. We want to somehow get rid of them or argue that they don't matter or something like that. And this has been done several times before in different settings. So there have been a few different approaches for dealing with these troublesome correlations. One approach, the original approach by Goldreich and Vigderson, was let's design just a special kind of randomized algorithm that has this special feature, which is that most random strings are good for all inputs simultaneously. And just to clarify, the reason that that's so special is that we also need the algorithm to use only up to n random bits. Okay, so that seems like a pretty special feature from a randomized algorithm, and so, no surprise, researchers have just been able to do this for a couple of specific problems. Ideally, though, we want to de-randomize a whole computational model or a whole complexity class. So one approach for doing that has been to design a special kind of randomness extractor. Okay, right? I mean, a randomness extractor is like a tool for cleaning up a low-quality source of randomness, or for getting rid of correlations in some source of randomness, which is exactly what we're trying to do. We're trying to get rid of correlations. So this should sort of make a little bit of sense that an appropriate kind of an extractor could do the job for us. And so researchers have been able to take this approach to de-randomize some really restricted models of computation, get typically correct de-randomizations for some restricted models of computation like sublinear time algorithms and two-party communication protocols. And then the third approach that's been used has been to design a special kind of pseudorandom generator. Because again, after all, we're trying to obtain random bits from our input. We're trying to generate randomness from that input. So again, I hope it makes sense that if we have a special kind of pseudorandom generator that's designed specifically for this purpose, then that'll do the job. And again, this has been used to get typically correct de-randomizations for some restricted models of computation like multi-party communication protocols. Okay, but for our result, we're going to use a new approach, none of these three, a fourth approach for dealing with these troublesome correlations between the input and the random bit. So here's our approach sort of on one slide, just a high-level view. The idea is we're going to use one teeny piece of the input as a source of random bits, while the algorithm is processing a different part of the input. Okay? So the basic reason that this ought to work is sort of embodied by this adage, out of sight, out of mind. Right? Remember, we're assuming that this randomized algorithm A is a small space algorithm. Right? So if the algorithm is looking over here at this part of the input, then it's already forgotten almost everything there is to know about this other part of the input over here. Which means that its behavior is mostly independent of this part of the input over here. So that's why we ought to be able to use this part of the input as a source of random bits. Yeah?
And most strings won't have correlations, right? Like if the string has had auto correlations, then
right.
You're allowed to have anomalous strings that you fail on.
That's right, but we only need a typically correct algorithm, so that's why you can sort of think of the string as being chosen randomly. Yeah. Okay, but that being said, if you're still not convinced, or if any of you is still not convinced, that's good. I mean, there's more to this presentation. We're going to need some further ideas to really make sense of this. But yeah, that's. Okay, so in order to get started on telling you, more precisely how this works, let me introduce this notion of like restricting an algorithm. So if we have a subset I of the indices, then we want to think of I as being like the forbidden region. This is where the algorithm is not allowed to look. Okay? So we'll define this restricted algorithm, the algorithm restricted to the indices outside I. So this is a new algorithm, and what it does is it runs the original algorithm, but if the original algorithm ever tries to read from this forbidden region, then the restricted algorithm just halts immediately. Just whatever configuration A was in, right before it read from that forbidden region, that's the final configuration, and the simulation is over. It's halted. It's kind of like, we're putting like Medusa at that forbidden region of the input, right? If the algorithm ever looks there, it's frozen. Okay, so this is sort of how we're going to enforce the fact that we're using one part of the input as a source of random bits, and meanwhile the algorithm is looking somewhere else. Okay, but I still need to tell you, like, if we're only using a small part of the input as a source of randomness, I need to tell you how we actually derive random bits from that part of the input. So, okay, let me first say, like, okay, I promised you a deterministic algorithm, right? But most of the work is actually going to be in just getting an algorithm that uses few random bits, a randomness efficient algorithm. Okay, so most of the work is we start with this super efficient randomized algorithm, and we want to simulate it by a randomized log space algorithm that only uses polylogarithmically many random bits. And of course, we only need it to be typically correct. And let me emphasize one point that might sound like kind of a technicality, but actually it's a really crucial point. So in this sort of the standard model of randomized space-bounded computation, the algorithm, we only get to read our random bits one time from left to right. Okay? So it's like if I'm a small space algorithm and I'm wondering about a coin that I tossed 10 minutes ago, well, I should have written that down and paid for it. So this is just this kind of technicality, but it's actually going to be really critical.
Actually, if I noticed correctly, your algorithm works even if the original one had two indexes.
No, it won't. We're going to require both. I mean, this one-way business. This applies both to the assumption here and to our algorithm. Yeah. Okay. So anyway, so like I was saying, we need to use this small piece of the input, and we need to somehow use it as a source of random bits. So the first tool we're going to use for this job is we're going to use a pseudorandom generator to stretch it out because it's not long enough after all. Right. So this is Nissan's pseudorandom generator, which you heard a little bit about if you were at Omer's tutorial yesterday. So this pseudorandom generator, it stretches a truly random seed of length log squared n. It stretches it out to a pseudorandom string, a long pseudorandom string. In our case, we're only ever going to need quasi-linearly many pseudorandom bits, so let's say that's its output length. Right, and it fools any log space algorithm. So in other words, you can use this in place of the random bits for any log space algorithm, and the algorithm would behave the same up to some tiny error. And Nissan's generator runs in log space. So you might be thinking right now, like, well, hold on, then doesn't this immediately achieve the goal that we wanted on the previous slide? Doesn't this immediately reduce the randomness complexity down to polylogarithmic, since the seed length is polylogarithmic? And the answer is no, not quite, because of this annoying technicality, which is that Nissan's generator needs to reread its seed many times. Okay? And we're shooting for an algorithm that only uses our random bits one time, from left to right. Okay? Still, though, we're going to figure out a way to make this work. I mean, that's why we're using the input as a source of randomness. So we want to get this seed from the input, but we are going to need to do a little bit of pre-processing to the input before we can really use it as a seed to Nissan's generator, because after all, we need to get rid of these correlations, right? The input, the algorithm might remember a little bit about whatever part of the input we're trying to use as a source of random bits. And so we're going to use another tool from the pseudorandomness toolkit, which is something called an averaging sampler. So this averaging sampler will output a seed to Nissan's generator, output like log squared n bits. And one way you can think about an averaging sampler, what it does is that it sort of it splits those random bits, those log squared n random bits. It sort of splits it into two parts. One part is short, so that's good. Short is nice because we can actually hold this in memory. And then the other part, okay, admittedly the other part is kind of longish, but the other part has this nice feature that it's good with high probability, like really, really high probability. Okay, so what I mean by that, just to be precise, what I mean by that is like, you can consider any function that's using these s bits and outputting an element of some potentially large codomain v. And the guarantee is that for most x, the first input to the sampler, for most x, the sampler like fools f in the sense that f behaves the same if you run it on a truly random input versus if you pick just a random second input to the sampler and consider that distribution instead. And quantitatively, like the number of bad x, once you've already fixed this function f, the number of bad x is only like, for the specific sampler I have in mind by Sheltiel and humans, the number of bad x is like 2 to the log to the 6th n times the size of this codomain. Right, so the number, compared to the number of all x, which would be like 2 to the log to the 100 n, right, the number of bad x is very, very small. And again, this algorithm runs in log space as long as it has, unrestricted access to its inputs. Okay, so now let me finally tell you how to combine these tools and get our main algorithm, the algorithm that proves the main limit, the algorithm that uses only polylogarithmically many random bits to simulate the super efficient randomized algorithm in a typically correct manner. Okay? So we're going to start by letting V be the initial configuration of A. Right? So by configuration, I mean like all the contents of memory and the state of the control. And we're going to proceed in like polylogarithmically many phases. So in each phase, we're going to simulate like a bunch of steps of A. So we're going to move this configuration V, we're going to move it forward through this simulation of A. So in one phase, what you do is you pick a random location in the input to use as a source of random bits. Okay, so we randomly pick a block of the input. And then pick a random seed of only log n bits. and then run this part of the input, run it through the sampler, and run that through Nissan's generator to stretch it out to a long pseudo-random string, Z. And then you feed Z into the restricted algorithm, the algorithm that is forbidden from looking at this part of the input. Right, so just as a reminder, that means that we're feeding Z into this algorithm and we're letting it run, we're letting it do its thing until it tries to read from this part of the input, at which point we just halt it, pause the simulation, stop everything. That's as far as we're going to go in this phase. Okay, and then we just store our progress in this V, the V variable, right? We update V to be whatever configuration this restricted algorithm halted it. Whether it halted early because the algorithm tried to read from this part, or the final configuration if this restricted algorithm actually made it all the way to the end of the computation. Okay, so we just do that for polylogarithmically many phases, and then that's it. We just accept or reject depending on this final configuration V that we're in. Okay, so let me do the efficiency analysis real quick. So here's the algorithm repeated for your convenience, right? And I claim this runs in log space, okay? Because we only need logarithmically many bits to store, this location I and the seed Y and the configuration V, right? Because it's a log space algorithm that we're simulating. And it only takes log space to run these tools, the sampler and the pseudo-random generator and the restricted algorithm. Right, and this sticky point, right, that Nissan's generator needs to reread its seed many times, that's okay. We can give it two-way access to its seed. We can give it full access to its seed because we're getting that seed from the input, X. And we have two-way access, we have full unrestricted access to our input. Right, we only get one-way access to our random bits, but we get full access to our input. Yeah, that's right. We can recompute Z every time we need a bit of Z. We can recompute the whole thing. That's right. Okay, and then of course this algorithm only uses polylogarithmically many random bits, right? Because there are polylogarithmically many phases, and each phase uses only a logarithmic number of random bits. Okay, so now let me tell you about the correctness of this algorithm. Hopefully, it's already a little bit intuitive based on everything I said to sort of motivate it, but let me just go through the argument quickly. So here's the correctness proof is like a hybrid argument. So we're going to have several steps, several hybrid distributions. Here's repeated the relevant portion, like what part of one phase of our algorithm. And the first hybrid distribution, the first step of the hybrid argument, is going to say well, let's get rid of the sampler. Just pick a truly random seed to Nissan's generator and plug it in. Now I want to argue that these two distributions are close for most values of X. Right, and the way we need to do that is just remember the guarantee of a sampler. It's defined in terms of some function that's using the output of the sampler. So let's let f of y prime be the final configuration you get when you feed, when you take y prime, you stretch it out using Nissan's generator and feed it into the restricted algorithm. Okay, then the number of bad x's can be bounded by, well, there's first, from the definition of a sampler, there are only 2 to the log of the 6th n, bad settings of the bits of x inside I. Right? Okay, and then, but that's, there are all those possible bad settings of x inside I. That's true for every possible setting of the bits of x outside I. So we just need to sort of union bound over all those. But there are only 2 to the n minus log of 100n. This is going to be sort of the dominant term. Okay, then we better union bound over all possible locations of I and all possible configurations that we're starting in V. But still, this is much, much less than 2 to the n, the number of possible inputs. So for the vast majority of x's, these two distributions are statistically close. Okay, and then the second step of the hybrid argument is where we just get rid of Nissan's generator. We just say, well, let's just consider picking a truly random string and feeding it right into the restricted algorithm. Well, okay, these two distributions are of course close for all x because that's Nissan's generator's whole purpose in life, right? Its whole job is that you can use it in place of truly random bits for log space algorithms. Okay, then the final step of the hybrid argument. For the final step, here's this right here was just one phase of this second hybrid distribution, and now we're expanding it back out so we have a whole loop. Right? And we want to compare that to the target distribution, what we're trying to simulate. And what we're trying to simulate is just the unrestricted algorithm. None of this restriction business. You just run the algorithm straight. So this is where we're finally going to use the assumed time bound on this algorithm A. Remember, we assumed that A runs in quasi-linear time, right? So this distribution on the left, this hybrid distribution, I mean, it's faithfully simulating the algorithm A. It's not like it's introducing any kind of biases into the process. The only thing that could go wrong on the left here is that maybe the computation never finishes because it keeps stopping early, right? And we only give it polylogarithmically many chances. So the only thing that could go wrong is that maybe we never actually make it to a halting configuration of the algorithm A. Right, but that's not very likely to happen because in each phase, I mean, this forbidden region of the input is only log of the 100 bits. So even if the algorithm A were looking for the forbidden region, I mean, it has no idea where it is. It's just guessing. It can't, it has no information about it. So it's going to take it, about n steps before it finally finds that forbidden region. So in each phase, with high probability, we make like almost a linear number of steps of progress through this algorithm. And the algorithm is only quasi-linear time, so after polylogarithmically many phases, we've completed the entire computation. That completes the proof of this main lemma. That shows how to reduce the randomness down to polylog. And now, like you might have heard a little bit from Omer yesterday, the rest of the job is not so hard. We use something called the Nissan-Zipperman pseudorandom generator, which will de-randomize any algorithm that uses only polylogarithmically many random bits. Okay? So that completes the proof. That gives us a deterministic algorithm just by cycling over all seeds to the Nissan-Zipperman generator. And so the only open question I want to ask is, we should be able to get rid of this quasi-linear time assumption. I want to typically correct de-randomization for all randomized block space algorithms. Thanks for your attention. Yeah, good question. Yeah, so the question was about... Yeah, good question. So the question was about a padding argument, right? If we can handle quasi-linear time algorithms, I mean, the natural thing to try is you start with any language in DPL. Well, if we pad it out, now suddenly it can be decided in log space and quasi-linear time, right? But padding arguments don't really play nicely with typically correct algorithms because after you pad out the input, now you have a very atypical input, right? If we just padded it with a bunch of zeros or something. So yeah, I mean, it's possible. That sort of sounds, though, like even harder than the problem of designing a pseudorandom generator for small space computation. So I'm not really sure how productive that approach would be. I mean, but yes, in principle, that would work.